Thank you for viewing our page on the Paradigm Challenge. We would like to present to you our idea for using nanotechnology for home fire prevention. In 2013, it was estimated that there were over 1 million fires in the United States, causing $11 billion in property damage and causing thousands of casualties and injuries. 85% of these injuries were caused in household fires. So it's not surprising that regulations require the use of flame retardants in household products. Flame retardants prevent materials from igniting, slow the spread of fire, and reduce combustibility. Although fires may seem like the most obvious danger, flame retardants themselves can pose a significant health threat. Children are especially vulnerable because their products, toys, and clothing are often coated with flame retardant substances, and they could also easily inhale dust that's lying on the floor. We will see why this is important on the next slide. We specifically looked at additive flame retardants. Additive flame retardants are added to a polymer after polymerization. Since they're not bound to the polymer chain, they can easily escape into the environment. This leads to buildup in household dust. As we said earlier, children and parents can easily inhale this household dust. We also see flame retardants persisting in landfills and wildlife, so humans are not the only ones affected by the use of flame retardants. These flame retardants have also been linked to thyroid cancer, neurological disorders, and decreased fertility. Now we move on to a really exciting part of our project where we used halloysite nanotubes. Halloysite nanotubes are naturally forming aluminosilicate clays, and they're non-toxic as well. They have a multi-wall hollow tubular structure, and we specifically used commercially treated halloysite nanotubes that were modified with tetrasodium pyrophosphate. The most important feature of halloysite nanotubes is that they could be loaded with small chemicals. A study done by Joshi et al. In 2012 shows us that halloysite nanotubes can control the release of and immobilize these small chemicals. In our previous research, we found that flame retardants could be absorbed and immobilized by HNTs, as Joshi et al. Predicted. We also found that treated HNTs were most effective for application in polymers from a study that we conducted ourselves. We specifically used Firol PCF, which is mainly used in polyurethane foams, and Firol Flex RDP, which is mainly used in plastic polymers. Additionally, nanoparticles have been combined with polymers before. Studies have shown increased thermal stability, tensile strength, and char layer formation in a plastic polymer known as EPDM. Similar results were also seen for polyurethane foam that was integrated with organically modified nanosilica. In our study, we'll be looking at both plastic and foam polymers. Rigid polyurethane foam has applications in thermal insulation, cushioning, energy absorption, etc. We also created a unique thermoplastic elastomer polybutylene terephthalate composite. This opens up a new area of research for this particular blend. These plastics could be used for insulation of wires. So our project intends to discover the feasibility of applying flame retardant treated halloysite nanotubes in foam and plastic polymers. Since halloysite nanotubes have been shown to improve thermal properties, combining them with flame retardants produces a synergistic effect. This is an overview of materials and methods that we use. So let's start with the loading of halloysite nanotubes. The halloysite nanotubes which we will now refer to as HNTs, and flame retardants were mixed with acetone and stirred overnight. We used the flame retardant PyroPCF for the foam polymers and PyroFlex RDP for the plastic polymers. The next day, acetone was separated using a vacuum. The samples were transferred into a vial and then centrifuged at 3,000 rotations per minute for 10 minutes. Finally, it was dried at 80 degrees Celsius for 2 hours. Moving forward, H&Ts will indicate the halloysite nanotubes immobilized with their respective flame retardants. So H&Ts immobilized with PCF were incorporated into rigid polyurethane foam while mixing the spray formulation for the foam itself. So while adding ingredients such as water, polyisocyanate, and polyol, we added our own H&Ts that were immobilized with PCF. Then we allowed the foam to expand, and finally we would cut the foam to dimensions that would fit our future tests. The sample containing 5% PCF by itself was our control. We also had a experimental sample containing 5% of PCF and 5% of H&Ts immobilized with PCF. The remaining experimental groups contained 5, 10, and 20% of H&Ts immobilized with PCF. Halloysite nanotubes immobilized with RDP were incorporated with TPE, or thermoplastic elastomer, and PBT, also known as polybutylene terephthalate. They were both incorporated with halloysite nanotubes using the heat extrusion process and the injection molding process. The heat extrusion process begins with halloysite nanotubes, the TPE, and the PBT pellets. They are added to the injection port and they are heated through the chamber. The heated material is carried through a water bath and finally is cut into evenly sized pellets. Now the pellets have to be added to the injection molder. Once again, the pellets are added to the injection port and heated, but this time the extruded material is loaded onto a piston that has a template inside of it. The template is formed and it creates different shapes. The circle is used for cone calorimetry. The 1.2 millimeter thickness rectangle is used for the limiting oxygen index test, and the dog tag is used for tensile strength testing. For the TPE PBT sample formulation, we have two different sets of groups. So we compare the TPE PBT composite without flame retardants and with 10% of our H&Ts loaded with RDP. We have a second group where the control is the composite with 50% of magnesium hydroxide. Magnesium hydroxide is a commercial flame retardant that is usually used in such plastic composites. Magnesium hydroxide is required at a 40 to 60 weight percentage of the composite. In this case, what we're trying to do is to reduce the amount of magnesium hydroxide needed so we could add our H&Ts and improve the thermal stability of the product.
The first test that was conducted is known as thermogravimetric analysis, or TGA. TGA measures mass loss as a function of time, so from these values, the thermal stability of a sample can be determined. We looked at the decomposition temperatures of all of our samples and found that the samples containing 5, 10, and 20% H&Ts took a higher temperature to degrade, which means they fared better than those with PCF, the regular flame retardant, and the combination. We also looked at cone calorimetry. In this test, a sample is ignited and several variables are recorded. We looked at heat release rate, which is the rate at which fire can be sustained. So both of these curves are very similar, which means that the 5% of H&Ts did not make much of a difference. However, the peak heat release rate for the combination of PCF and H&Ts was better than just PCF. There was also a secondary peak with the PCF and H&Ts, which means that there was a less stable char layer formed, although not by much. Now comparing the 5, 10, and 20% H&Ts, the 5% H&Ts had the highest peak heat release rate, which is an issue. However, this char layer formed afterwards was fairly stable. And then there's slight differences between the 10 and 20%, but it seems that 5% was the most stable after burning. Next was thermomechanical analysis, which shows how the structure of the foam was affected based on temperature. So the foams that remained at higher heights at higher temperatures were more structurally stable. Our results showed that the 20% H&Ts had the most stable structure, as they did not degrade till much higher temperatures than the 5 or 10% H&Ts. With comparing the 5% PCF and the PCF with the H&Ts, they were fairly similar, with PCF showing slightly better thermal stability. The final thermal test that was conducted was the limited oxygen index, which shows the minimum amount of oxygen required for a material to combust. The line represents the amount of oxygen that is normally in the atmosphere, which is around 20.95%. As the graph shows, the H&Ts fared slightly worse than the PCF. However, with increasing quantities of H&Ts, the LOI improved, which was a good sign. Now we move to the limited oxygen index with the plastics. As you can see, the addition of H&Ts with the magnesium hydroxide infused composite significantly improved its LOI, making it very difficult to ignite. So the H&Ts and magnesium hydroxide was the best by far. Next is the thermogravimetric analysis for the plastics. The plastic and the plastic with 10% H&Ts had a very similar decomposition temperature. However, the 40% magnesium hydroxide and 10% H&Ts had a higher decomposition temperature than the just 50% magnesium hydroxide, as you can see here. Next is cone calorimetry for the plastics. And for both cases, the adding of 10% H&Ts actually reduced the peak heat release rate for the sample, which means it burned, the highest temperature it burned was lower. And as you can see, this is also evident in the magnesium hydroxide samples. Overall, H&Ts had different effects at various weight percentages. At higher percentages, there was an increase in LOI, thermal stability, and hardness, as well as a lower peak heat release. At lower percentages, however, there was a stronger char layer formed and also a lower average heat release, which shows that there are different applications for different weight percentages of H&Ts. The combinations of H&Ts and flame retardant was also very effective. These samples had higher thermal stability, lower maximum burning temperature, and improved structural properties, showing that there are great advantages and applications for the combinations of our H&Ts and currently used flame retardants.
Our study shows that the addition of halocite nanotubes had a synergistic effect with the flame retardants, in that it improved the flame retardant and structural properties of the polymers, and it worked well with current flame retardants. Since we used the flame retardant treated halocite nanotubes in two different polymers, we are demonstrating its potential use in a huge variety of products. We can also show that our flame retardant treated halocite nanotubes can be used in commercial applications. Our project has significance for three major audiences. First of all, for the consumers, because we are preventing them from being exposed to the toxic flame retardants while they are still protected by the fires. Secondly, manufacturers will find this very appealing because halcite nanotubes are very cost effective and they have shown to improve polymer properties by themselves. Additionally, it reduces the need for other flame retardants in polymers, as we have shown with the magnesium hydroxide. By reducing the amount of flame retardant needed for the polymer and by adding halcite nanotubes, we are once again lowering the cost for manufacturing. Finally, this is very beneficial for the environment because the entrapment of the flame retardants inside the nanotubes prevents the natural leaching, abrasion, and volatilization that occurs with products that contain flame retardants. And secondly, we are reducing the amount of flame retardants found in the environment, including wildlife, landfills, and households, where it could be easily inhaled by one of you or your family members. For our future work, we want to perform our own modification of the halcite nanotubes to create a more effective treatment. Commercially treated halcite nanotubes were treated with tetrasodium pyrophosphate. We would like to try our own treatment with 1-decyl phosphonic acid. This essentially reduces the amount of decomposition products and the number of reaction sites, so that the flame retardants are only being added and not reacting with the hollow tubular structure of the halcite nanotubes. Secondly, we would like to analyze the halcite nanotubes loaded with flame retardants using electron microscopy. Specifically, we would like to use a transmission electron microscope to show clear evidence that the flame retardants are trapped inside the nanotube. We would like to acknowledge our mentor, Dr. Sing-Chan Peck, at Israel Chemicals Limited Industrial Products. We would also like to thank the Head of Research and Development at ICL, Dr. Sergey Levchik, our Pelham Science Research Director, Mr. Stephen Beltegas, our parents, and our local community. These are our references. These are our references continued. Thank you for visiting our page at the Paradigm Challenge, and please don't forget to vote. Thank you.